Every second, the sun gives us enough energy to power the planet. So, why can't we catch it all? Hi, I am Fatina, and I am joined by my team members Dr. Muhammad Zaki, Madam Madia, Dr. Siti Aisha, and Sir Baba Hussein. It's all about improving solar cells, making them smarter, stronger, and more efficient for the future of clean energy. The innovation we developed is presented under the title Next-Gen High-Efficiency Zinc Oxide Gallium Arsenide Solar Cells with Advanced Double-Layer Anti-Reflective Coating or DLARC engineering. How can sunlight be turned into electricity? The answer lies in the photovoltaic effect. When sunlight reaches the surface of a solar cell, it carries energy in the form of photons. These photons strike the material inside the solar cell and excite the electrons. When this happens, the electrons break free from their positions, leaving behind what we call holes. The electrons and holes then move in opposite directions through the layers of the cell. This movement creates an electric current, and that's the electricity we can use to power devices. Before we move into our innovation, let's look at common solar cells. The first is silicon, the most widely used because it's abundant and low cost, but its efficiency is limited. Next is zinc oxide, often used as a transparent conductive layer, cheap and eco-friendly, but less efficient on its own. Lastly, gallium arsenide, which offers high efficiency and works well even in low light, often used in satellite. Each has pros and cons, so researchers combine them in heterojunction design to get the best of all worlds. And that brings us to our innovation, the zinc oxide gallium arsenide solar cell. In recent years, the combination of zinc oxide and gallium arsenide has attracted the attention of many researchers. This is because both materials have characteristics that make them an excellent match. Zinc oxide is a transparent material that allows sunlight to pass through easily. Gallium arsenide, on the other hand, has a direct bandgap and very high efficiency, making it one of the best semiconductors for solar energy conversion. When paired together, zinc oxide and gallium arsenide complement each other very well. However, the optimization of this device is still ongoing. Researchers have not yet identified the best values for thickness, doping concentration, or configuration to achieve maximum efficiency. This leaves a huge opportunity for further study and innovation. However, there was a problem that usually occurs. Light has natural behaviors such as reflection, refraction, interference, and diffraction. These are normal physical processes when light interacts with any surface. The main issue for solar cells is reflection. When sunlight strikes the top surface of the solar cell, a significant portion of the light is reflected back into the air instead of entering the cell. In simple words, more reflection means lower efficiency. To overcome this issue, one effective method is to use an anti-reflective coating on the surface of the solar cell. So how? When sunlight hits the ARC layer, the coating creates a condition where the reflected light waves from the top and bottom surfaces interfere with each other and cancel out. This phenomenon is called disruptive interference. By reducing refraction in this way, the ARC allows a greater portion of sunlight to penetrate into the cell, which significantly improves the overall efficiency. Now, let's talk about the characteristics of anti-reflective coating or ARC. The first factor is the choice of materials. Different materials have unique properties, and this strongly affects how well they can reduce reflection. Next is the number of layers. Using multiple ARC layers helps capture light across a wider range of wavelengths instead of just one. Finally, refractive index and thickness are very important. This must be carefully calculated so that disruptive interference happens at the right wavelength, which minimizes reflection and lets more light enter the solar cell. We designed our final device, a zinc oxide gallium arsenide solar cell with a double-layer ARC made of silicon dioxide and zinc oxide. By adding silicon dioxide and zinc oxide as a double-layer ARC, we can reduce reflection even more effectively compared to a single-layer coating. Silicon dioxide has a low refractive index, while zinc oxide has a higher refractive index. By stacking them together, they create a gradual transition of light entering the cell, which minimizes reflection across a wider range of wavelengths. To study and test our device, we use a simulation software called PC1D Simulation. PC1D is a program that allows researchers to design and model solar cells on a computer. Instead of building the solar cell physically, which can be expensive and time-consuming, we can simulate its behavior under sunlight. This is how the parameters of the substrate and ARC's materials that has been used in the simulation. Using PC1D, we simulated our zinc oxide gallium arsenide solar cell with and without using double-layer ARC, and here are the results we obtained. The efficiency was increased from 17.76% to 19.64% after applying the ARC. For the percentage of reflectance was drastically decreased from 10% to 0.805%. For future work, there are a few possibilities to improve the solar cell. First, we can optimize the doping and thickness of zinc oxide and gallium arsenide to boost efficiency. Second, we can test other materials for ARC beyond silicon dioxide and zinc oxide. Third, we can design multi-layer ARC to capture light across more wavelengths. And finally, we can explore methods like a surface texturing or nanostructures to further enhance light absorption. This shows that our research is just the beginning, with many ways to move toward higher efficiency solar cells. We hope that this research can contribute to the development of clean and sustainable energy for the future. Thank you for watching our presentation, and we truly appreciate your time and attention. From sunlight to solution, power the future, protect the earth.